Good evening, advanced higher physics students. Welcome to our second advanced higher hangout. Tonight, I'll be giving you maybe about 4 or 5 starter questions. You can watch live. You can do the calculations along with me or the derivations of the formula along with me and keep up the revision. If you're watching later on YouTube, you can simply just watch the start of the question, pause the video, and then see the answer or the solution after it. As always, I'll be going to screen share in a wee minute to give you the start of the questions. But if there's any questions you want to ask after this hangout, then please feel free to put the answers down at the side of the page or the group chat, which is at the side of the page, and I'll pick it up a wee bit later on. So let's begin this next half hour with 4 or 5 starter questions. I'll now go towards the screen share button and we shall start our revision questions for tonight. Now there's the first question we have tonight. It appeared in your prelim and it was starting with the expression below for the angular acceleration. Derive an expression for the angular displacement theta. And all you're given is really the angular acceleration equals d2 theta by dt squared. Well, we have to know first of all to be able to split this up. So we can rewrite that as the following. We can say d by dt of d theta by dt. And if you do advanced maths, you should be quite comfortable with that. But we know that d theta by dt is really equal to omega, the angular velocity. So right away we can change that to d by dt of omega. So d omega by dt. So our big expression here comes down to angular acceleration equals d omega by dt. Now the initial conditions in this example is that at a time t equal to 0, we have omega equal to omega naught and theta, the angular rotation, equal to 0. Now we've got angular acceleration alpha is going to equal to d omega by dt. So we can cross multiply and we can have d omega is going to equal to alpha dt. Then we begin to integrate up. So I can say the integral of d omega equals the integral of alpha dt. Now, what does that give us then? Well, quite simply, it gives us omega for integrating up d omega, and alpha dt becomes alpha t. So omega then equal to alpha t, plus we have to put in a constant. Now, how do we find a constant? Well, we know when time t equals 0, the initial angular velocity is going to be omega naught. So omega naught is going to equal to 0 plus c, which implies then that c is equal to omega naught. So we've now derived our very first question, our very first expression, sorry, and that is the following. It is this one here, if I can get the pen again. It is omega is equal to omega naught plus alpha t, omega being the constant. But the question is asking for us to derive an expression for the angular displacement. So we have to use the fact then that omega is d theta by dt. And that means that's going to equal to omega naught plus alpha t. We'll just put a little bracket around that to keep things tidy. Cross multiply again, and we have the following expression. We have d theta. It's going to, sorry, I'll rub that wee bit out there. We have d theta is going to be equal to omega naught plus alpha t dt. So we have got an expression to integrate up. So the integral of d theta should equal the integral of omega naught, I'll put that in a bracket again, plus alpha t dt. And as usual, initial conditions. So we have theta is going to equal to omega naught t, that becomes a t, plus 1/2 alpha t squared, integrating alpha t up, plus, and we have to put in a constant c. But we do know that when t equals 0, we have the following. When t equals 0, we have theta, the angular rotation at that point in radians, is going to be equal to 0 as well. So that would imply that the constant is going to equal to 0, because we're going to have 0 equals 0 plus 0, and the constant must be 0. So finally we have our final expression for the angular rotation. Theta is omega naught t plus 1/2 alpha t squared. And it's the same, almost the same expression for the linear equivalent of displacement equals ut plus 1/2 at squared. So the angular equations is very much the same as the linear equation as well. In fact, almost identical. So learn that proof, because you could be asked that, and you could be asked it from first principles, as they say, and that is starting off with alpha equal d2 theta by dt squared. And that's the link which I think most people in the prelim fail to sort of jump onto and cause that wee bit of problems for you. So replay that question and double check that you can prove those equations from the start. Okay, next question is to do with NASA. It's to do with this picture here of a centrifuge. And a centrifuge is a piece of apparatus built in this big room here, 20 meters in radius, which spins round in a circle round this room like that. And it's designed to give an astronaut who is sitting in some sort of chair here. There's the astronaut sitting in there, if I can draw him. And he's going to spin round. And it's to give the astronaut the practice of experiencing very big accelerations that you'd actually encounter during takeoff of a rocket. And in this case, the astronaut is going to experience a horizontal force of 5g. Now, what does 5g mean? 5g means 5 times the astronaut's normal weight on Earth. So this big contraption will spin round here and give that astronaut the feeling that he's 5 times heavier than what he was, or press him 5 times more into his chair as what normal gravity would. And the question is, calculate the angular velocity of the centrifuge in this particular case. So how are we going to do this one then? Well, we start off by knowing that anything is in circular motion, and that's going round in a circle here. We know that there must be a force present to give the centrifugal force. And we know the centrifugal force, a well-known phrase and a well-known equation, is mv squared divided by r. V being the tangential velocity, going around the circle, and r being the radius, in this case 20 meters. So it's the force provided by the chair which is going to be responsible for the centrifugal force. So the force pushing the astronaut into the circle comes from the chair. And that chair is going to give him a force of 5g. So the force which the astronaut experiences 5 times his weight, so it will be 5 mg, will be the astronaut's force experienced, and that will be equal to mv squared upon r. And we're asked to find the angular velocity, omega, in this particular case. So first of all, we'll try and work out what the tangential velocity is, because we know that the tangential velocity v equals omega r, and if we can find v, it's a simple case of finding omega, the angular velocity. So that's the equation we're going to be dealing with. You can see things cancel out, the m cancels out, and we cross multiply with the r. We're going to get 5g times r is going to equal to v squared. So we could just simply rearrange that to give us what v is. V is going to equal to the square roots of 5 times g times the radius. So that's going to be a simple calculation to do. 5 times 9.8 times the radius, and the radius is going to be 20 meters. Then we take the square root of that. So 5 times 9.8 times that is going to give us an answer roughly about 31 meters per second. So he's going to be travelling around tangentially at 31 meters per second. So what's the angular velocity? Well, we know from our equation v equals omega r. That implies that v divided by r is equal to the angular velocity. So 31 meters per second divided by the radius, 20 meters, and that's going to give us the angular velocity, which comes out to be about 1.6 or 1.56 radians per second. So we also can find out how many revolutions per second the centrifuge goes, because we know that in one revolution is going to be 2 pi radians. So we're going to go 1.6 radians per second. You can easily go and work out then the actual angular rotational, how long it takes to do one particular period. And I'll leave that up to you to do that for yourself. So finally we've got an answer for that one in. The angular velocity is 1.6 radians per second. Okay, let's move on to our third question for this evening. Doing quite well. And it's this one here. It's to do with the travelling wave. And the travelling wave is represented by the following expression: y equals 0.05 sine bracket 50t minus 20x. And from that information here, we have to determine the frequency of the wave, the wavelength of the wave, and finally the speed of the wave. Now, in this particular case, you have to know the link, and that is the linking information here. And the linking information is quite simple. It says y equals a sine omega t minus kx is the expression for a travelling wave moving to the right. And this number k is 2 pi divided by lambda. When you go further in physics, you'll find out that number k is actually called the wave number. You won't need to know that for the higher, but that's actually called the wave number. K equal to 2 pi upon lambda. Now, this particular type of problem is a good problem to do in advanced higher, because all you have to do is look at the expression and compare things. And right away we can see that the amplitude of the wave has got to be 0.05. So I can put down there that the amplitude of the wave, amplitude of that wave, although I'm not asked for it, but the amplitude is going to be 0.05, 0.05, and we presume it's going to be in meters. What's the frequency of the wave? Well, we compare omega t with 50t, and that must mean that omega is equal to 50. Now, what is omega? Omega equals 2 pi f, so 2 pi f is going to equal to 50, and therefore we can see that the frequency is going to equal to 50 divided by 2 pi, which we can simplify down to 25 over pi. Now you can do 25 divided by pi in your calculator to get the decimal answer, but I'll just leave that at the moment as 25 over pi hertz. Our next question is, what's the wavelength of the wave? Well, that's where we get the information in this part. K is equal to 20, so therefore we have 2 pi over lambda has got to be equal to 20. It's so easy. This is an easy question to do, as long as you remember our travelling wave equation and compare things on both sides. So 2 pi over lambda equals 20, and therefore we can see that we cross multiply lambda must be equal to 2 pi over 20, which is equal to pi over 10 meters. And we'll leave that answer in pi form at the moment. The final question is asking us find the speed of the wave, and we know from our standard grade years, our basic physics, the speed of a wave is the frequency times the wavelength. So if we get to know all the information we've got here, we have 25 over pi hertz for the frequency and pi upon 10 meters for the wavelength, then it's straightforward, easy to substitute. Frequency 25 over pi multiplied by the wavelength, which is pi over 10. You can see why I've kept it in terms of pi's, because it's easy to calculate. You can do it both ways. decimal or this way, it still gives you the same answer. So 25 over pi times pi over 10 is going to reduce to 25 over 10, and therefore the speed of that wave is 2.5 meters per second. Now that's a very good question to do in the Advanced Higher. It's one which picks up your marks. All you have to know is remember this important piece of information here. You'll probably get it. I think it is in the data book. Y equals a sine omega t minus kx. Omega is linked to the 50. K, the wave number, although that's a wee bit advanced in the future, but we'll write it as 2 pi upon lambda. 2 pi upon lambda is 20. You can solve it and you can get your answer for that. A very good question to do in the Advanced Higher. So practice that one. And if you go into the Desmos site, you can make up equations of yourself like that and actually see the number of waves and amplitude for yourself if you go to the Desmos site on the web. Good question there. Let's see what's awaiting us for our next question. Oh, it's Robert Millikan. And Robert Millikan is the man who ruined his eyesight by spraying little droplets of oil into a container which had one plate held very positive, another plate held very negative. And there he is there, without his glasses, looking through a microscope and focusing in on one particular drop of oil. The experiment was a wee bit more complicated than that because he could vary the potential difference between these plates, and he could see which of these oil drops were moving up and down. So what was this experiment all about, and what could they ask you in the Advanced Higher? Well, they could ask you this particular question here. They could ask you to find the charge on the oil drop. Now, an oil drop is sprayed. These are sprayed at a small bottle here, some device that sprays them out. They acquire an electric charge due to friction. And the electric charge, then the oil drops fall through, but some fall through a hole and enter into what we call the electric field. Now, when you enter into the electric field, this will be the particular data you might be given. The potential difference between the plates, distance between the plates, and of course the mass of the oil drop. That's found by a method of watching the oil drop reach terminal velocity and then doing a few calculations and finding the mass of the oil drop. In the Advanced Higher, you'll just be given the mass of the oil drop, or maybe even asked to find it. But let's look what happens to one of these oil drops in this electric field. We're in an electric field, between these two plates, an electric field, which we'll call E. That's the electric field. And there's a potential difference between the electric field, the two plates. We'll draw the potential difference in here like that. Potential difference is V volts. And we know that there's a distance between the plates, which we'll call D, being a distance between the plates. We've got that at 16 millimeters. But let's focus in on the oil drop itself and see what forces are acting on the oil drop. Because if we've got the oil drop like that, we know right away one of the forces acting on it is good old gravity. Weight pulling it down like that. So that's going to be the weight of the oil drop. Weight equals mg. But because the oil drop is negatively charged, it will experience a force towards the positive plate up here. So it's going to experience a force which is going to pull it up the way. Oh, sorry, probably not right. A force which is going to experience up the way, and that force is going to be equal to the electric field times Q. So it's going to experience an electric force which is equal to the electric field times the charge on the oil drop. Now these two forces will be equal, the oil drop will be balanced, and good old Robert Millikan, well, one of his undergraduates, will be looking at that oil drop and making sure it's stationary. But it's when it's stationary these two forces are the same, or when it's moving with constant speed. So let's equate the forces then. Mass times gravity. The weight should equal the electric field times Q. But we do know the electric field in a uniform electric field between two plates. The electric field is given as the potential difference divided by the distance between the plates. So we can rearrange that to give us mg is equal to vq all over the distance in the plates. We're asked to find what the charge is q. So q, if we rearrange, cross multiply, is going to give us mg times d divided by the potential difference of between the two plates. So that's that one done there. And if we plug in the numbers, we'll see what we get. The mass of the oil drop is going to be 4 times 10 to the power minus 14. You can do this calculation as we go along. Times 9.8 multiplied by the distance between the plates, 16 millimeters. And to change that, we just have to go 16 times 10 to the minus 3 meters. Divided by the potential difference. The potential difference V is 7,850 volts, which is going to give us, if we do the calculation, is going to give us about 7.98 times 10 to the minus 19 of a coulomb. So that's the charge on the oil drop. Now, what was Robert Millikan very famous for? He did this experiment and he found out a very important thing. He found out that electric charge was quantized. That was the main reason for his experiment. His charge, the electric charge, was quantized. Now, what does that mean? It just simply means that charge comes in lumps, certain amount of lumps. Quantized means comes in packets. So if you've got 7.98 times 10 to the minus 19 coulombs of a charge on this oil drop, we can find out how many excess electrons is on it. The number of excess electrons can easily be found. Excess electrons rubbed onto the oil drop as it went through the spray will equal to 7.98 times 10 to the minus 19 coulombs divided by the charge on one electron, which we know is 1.6 times 10 to the minus 19 coulombs. And if we do that in my calculator, 7.98 divided by 1.6, it's about 4.98, which is roughly equal to 5. 4.98 roughly equal to 5. So that experiment tells us that when we sprayed the oil drop through the sprayer, one of that oil drop there received an excess charge of 5 electrons. So there he is, good old Robert Millikan, his famous experiment. Get to know how to draw the forces in the diagram, get to know how to rearrange. This is the little part here which people forget. The electric field in a uniform electric field is V divided by the distance d, potential difference divided by d. That's the bit people forget. Rearrange, and that's you got it. So, Robert Millikan, we salute you, finding the charge to mass ratio of electron, find the charge on the electron. Okay, let's move on to our next question. We're doing very well this evening. Okay, it's a simple one. It's to do with gravity. The minute you see one of these questions, you should be absolutely delighted that you've got a gravity question. So let's read out what it's about. Show that the gravitational field strength at the surface of the Earth is given by G equal to the universal gravitational constant times the mass of the Earth times divided by the radius squared. So let's look at a mass which is sitting on the surface of the Earth, and we know the gravitational field strength at the surface of the Earth is going to be mg. So we know that's going to be mg, mass times gravity. But in terms of the gravitational field strength, we go from the centre of the planet out to that point, and that will be a distance r. We'll call that a radius r. And remember, the gravitational force is taken from the centre of the planet, and the gravitational force we know is going to be equal to G, universal gravitational constant, times the mass of the small mass, which is m, times the mass of the Earth, divided by r squared. Now both must be equal. So the gravitational field strength at the surface, which we know is mg, well, that must be definitely equal to G small m big M E divided by r squared. and nothing could be easier because the two m's cancel out and you're left with the gravity G can be found to be universal gravitational constant times the mass of the Earth divided by r squared. So that's quite an easy one to do. Just rehearse that, practice all these ones with the universal gravitational constant in them and the force of gravity, and you can't go wrong. The only thing you can go wrong in is forgetting you've got to go from the centre of the Earth. So, good question there, and that's one which is quite easily done, and a good one. I'll leave you to think this one out. You can maybe think this one through for yourself. If we plotted a graph of r with the gravitational force, what shape of graph would it be? Assuming that's us starting at the radius of the Earth here, that's us going out here. That bit in here is the radius of the Earth. So before the dotted line would be the radius of the Earth, like that. So what would be the shape of the graph? Well, from our previous studies we know that for a big mass the force is going to go straight up like that inside the Earth, but once you leave the surface of the Earth it's going to tail off as 1 upon r squared. So 1 upon r squared outside the surface of the Earth and proportional to the radius inside the Earth. So that's one to keep up your sleeve in case they ask you the graph. That part would be quite easy, the 1 upon r squared, because we get that from here, but this one here would be a wee bit hard to remember. Okay, so we've now moved on quite far and on to our last question for this quick hangout of revision. I hope you're enjoying it so far. And here is a very special gentleman. He's called Louise de Broglie. There he is, Louise. That's not his signature. It's me writing on it. Louise de Broglie. He was a prince, and he's got a very happy smile on him because he's got a happy smile because he's just left a lesson on how to work out the interference of thin films in a bubble, as we did today. So you can see that he has got one happy smile because he has understood it. What a tough lesson that was today, but we got there. But back to the question in hand. It's de Broglie, and what did he say? He said that particles that have momentum, they have a wavelength. So what he was saying was particles have a wavelength, and we don't want to get into the big argument about particles and waves. We've got to be very consistent and say that there's a particle-wave duality. Particles do have waves associated with them. There's a whole big physics behind that. But let's go to the problem here then. We know that de Broglie said the wavelength associated with the particle was equal to h divided by p. H is Planck's constant, which is 6.63 times 10 to minus 34 joule seconds, and that these electrons will be accelerated through a potential difference of 2.5 kilovolts. So to find the wavelength, we have to find the momentum of the electrons first of all. And we're told the charge on the electron is this, and the mass of the electron is that then. So how do we find out the speed of the electron first of all? Well, let's go back to a higher class, and we know that the charge on the electron is E. If it passes through an electric field, it's going to gain E times V energy. The field does E times V work on the electron, and that will appear as kinetic energy. So EV will be equal to 1/2 the mass of the electron times the speed of the electron. And therefore we can rearrange that to find out what the speed of the electron is. We just multiply the EV by 2 EV, and we divide that by the mass, and we take the square root, and we can find the speed of a charged particle as it passes through a potential difference that we're given. So we put the numbers into that one then, we can easily find out what the speed is. Just move the page up a wee bit. We can find out what the speed is. It's going to be 2 times the charge on the electron, 1.6 times 10 minus 19, times 2.5 kilovolts, 2.5 times 10 to the power 3, divided by the mass of the electron, very, very light, 9.11, times 10 to minus 31, and we have to take the square root of that. Now if you do that calculation, hopefully it's not going to be relativistic. It's not going to be anything near the speed of light or anywhere near it, a tenth of it. So we do the calculation, we end up with 2.96 times 10 to the power 7 meters per second. So we've got the speed of the electron. If we have the speed of the electron, we can find its momentum. So over here we can say momentum is equal to the mass times the velocity. The mass of the electron is 9.11 times 10 to the minus 31, and we've got to multiply that by the speed, which worked out to be 2.96. Squeeze this in here, times 10 to the power 7 meters per second. So that's the momentum of the electron. So the wavelength of the electron is going to be equal to Planck's constant divided by the momentum. So we take Planck's constant, 6.63 times 10 to the minus 34 joule seconds, divided by the momentum, which we've worked out there hopefully, 9.11 times 10 to the minus 31 times 2.96 times 10 to the power 7. And if we work that out, we'll get the wavelength of the electron. I'll leave that for you to do yourself. And that's the wavelength of the electron. So good old de Broglie, there he is there. Lambda equals h upon p, and you can work out the wavelength of the electron from that. Okay, so where are we now then? So we've now come to the sort of kind of end of our Hangout. So if I can find out how to get back here, stop sharing, and go back onto the screen. So hopefully you have enjoyed that Hangout there. I don't see any people making me chat on here just in case you had a question, but that's okay. Hopefully we'll continue this questions tonight between now and a way back when the exam comes. So I hope you've enjoyed it. I hope you've got something out of tonight's half hour. And I hope you keep up the good work. I'll post some revision questions on Edmodo either tonight or tomorrow to get us ready for our NAB, which is coming up on March the 12th. Anyway, from Mr. Marlon, I hope you've enjoyed this Hangout, and take care. We'll see you tomorrow. See you next day on Thursday, and hopefully we can go back over that thin film equation again. That will make you really happy, that one then. Thanks very much for watching. Thank you.